What's cracking, guys? In this video I'm going to cover a very interesting paper, and as a quick note, I still don't have, as you can see, I don't have the video and the YouTube studio set up yet, so I'm going to have to only show you the paper for the time being. Hopefully I'm going to solve that very quickly. But basically I'm covering this novel, very interesting paper called Efficient Geometry Aware 3D Generative Adversarial Networks, or GANs for short, from this beautiful group of people from Stanford and NVIDIA. As a quick note, I think that the very fact that this is 3D, I think this is a pleonasm, because 3D should imply the geometry aware part of this title. But yeah, in any case, I guess it makes for a more interesting title. Okay, before I start digging into the actual paper, let me show you their video.
We present a new 3D GAN that produces photorealistic images that are both multi-view consistent and geometry aware. Our approach enables unsupervised learning of high-fidelity 3D representations without any explicit 3D or multi-view supervision.
So you can see results are fairly impressive because they are multi-view consistent. You can see that even when you're changing the poses, the appearance and the identity remain the same, which is kind of tricky for GANs to achieve. And you can see that. So here, what's interesting is you can see. Let me stop it here. You saw that the texture is kind of sticking, and so when the cat is moving, when the pose is changing, you can see that the fur is kind of flickering or something. So that stickiness problem, I think it's called like that, like texture sticking problem, was solved in one of the newer style GAN papers, if I'm not wrong. Okay, in any case, let's get back to the paper. We saw the visualizations there, and now let me try and explain why this paper is special and very interesting. So first thing they say here is that they trained this whole thing, this GAN, without any ground truth 3D scans or multi-view supervision. So that means they just have 2D images basically, and they managed to achieve this basically multi-view consistency. As you can see here, the pose here changes, but the identity remains the same. And they also managed to recover the underlying 3D geometry of the scene, which is very cool. Now, in order to understand how this paper works, we have to start with this novel explicit-implicit representation they devised called tree-plane. I think it's called tree-plane representation or something. But basically, it's a combination. It's somewhere in the middle between NeRF, and I'm gonna shortly explain what NeRF exactly is, and these explicit voxel approaches. And when you combine the good sides of this approach and the NeRF approach, you get this novel representation that they've devised. So the main idea here is that the thing with NeRF is that it's memory efficient, let's call it that way. So the memory is cheap, but the inference is very expensive. So if you wanna run this thing, if you wanna get the density and color from a certain point of the scene, you're gonna have to do a forward pass, which is way costlier compared to, for example, this voxel approach. So where here, as you can see, you have to explicitly keep the representation in a form of this cube, and that means it's memory expensive. But on the other hand, the actual querying is very fast because you only have this shallow MLP part here. So combining those two, they get the representation here. But this probably won't make any sense if you're not familiar with NeRF or these other previous approaches. So I'm gonna do a quick digression here and explain how the NeRF paper works in detail. So NeRF is very interesting paper, and basically there was a Cambrian explosion of papers that came after NeRF that tried to improve upon various elements of NeRF. But here I'm going to explain the original architecture itself. And the thing that's very funny and there is a paradigm shift here, and that is that overfitting is actually good in NeRF. So NeRF basically overfits, like heavily overfits to a 3D scene. So you can see a bulldozer here as an example. So it heavily overfits to that scene such that basically you can query this scene from a specific, you take a specific point and you basically pick like a direction vector, and it will give you the pixel color from that position and that direction, which is kind of fascinating. So you can query this 3D scene after you've trained the NeRF, and I'm going to explain how that works in a second. You can query it and get like these images. You can see this one here or this one here. You can get the same thing from some another spot. Like you can maybe place a camera here. You place a camera here. I'm going to just depict the camera as this triangle, and you get a novel image that you can just kind of get by querying the MLP, the multi-layer perceptron that was trained and overfitted to this 3D scene. So let me try and explain very briefly how NeRF works. So you basically have a sparse sampling of the 3D scene. And what I mean by that is that you have images such as this one. So this is image number 1 taken from this particular location here. Let me try and change the color. So we have from this location, there was a camera here and somebody took the image, and then there was a camera here and we have associated image. So we have associated images and poses, and it's very sparse. Like you maybe have 30 or 40 different images of this scene. And now what NeRF does is the following. You train the NeRF the following way. Basically, NeRF takes as an input this x, y, z. So that's a coordinate. So that's basically a position. So for example, I want to place a camera here. So that's the position of the camera. And then you have the theta and the phi, which are the angles. They basically determine the ray, the vector in the space, starting from that particular point in space. And so once you input that tuple, that n tuple into MLP, it basically outputs like the 3-dimensional vector that represents the color, so the RGB vector, and this sigma thing, which is called density, volume density, basically. So what volume density represents is basically the probability that the ray has stopped at that particular point in the scene. So think of that like this: if you had a ray like starting from here and radiating through the scene and passing through the bulldozer, once the ray touches the surface of this part of the bulldozer and enters the actual bulldozer, you'd expect the sigma to go up, because basically you will not be able to visualize that point because it's internal to the bulldozer, and so the volume density kind of spikes up. And you can see those rays. So this is a visualization of the thing I was just mentioning. So you take a ray like ray 1, so that may be this red line here, so that red line here, and you can kind of visualize the volume density here. And now how NeRF works is you take a bunch of points along a certain ray. Like you can see these black dots here. You query the MLP, so this thing that's like a part of NeRF. And so that basically MLP is the thing that learns inside of this NeRF framework. And you query it alongside all of these points, and you get the RGB sigma vectors. And then what you do is, using sigma, you do a weighted average and you get the final color. And that's how they kind of visualize that here. So you basically will have some aggregate of these values, and you're going to form a color, and then you're going to do a simple MSE loss, so mean square error, using the ground truth pixel value. So you have the ground truth because you have the image. So for example, here it's going to be, let me change the color again. Let me see, let me pick blue, whatever. So you'll have a yellow pixel here, and whatever came from this summation here, you want to make sure to push it towards that point here. And that's the whole trick. So how you train like NeRF is you take a bunch of these rays. So remember, we have a sparse sampling of this 3D scene. We'll have a bunch of these images. We'll take some rays emitting from the cameras from those images, and we're gonna do this sampling alongside those rays. We're gonna form these colors, as you can see here, and we're gonna do the MSE loss. And we're going to do this only, like, we're gonna basically overfit like crazy to this 3D scene. So once that's done, you can basically query NeRF from some unseen position. Like, as I said, you can maybe place a camera here or whatnot, and you can get a 2D representation of this 3D scene from that particular pose. And that's amazing. I mean, you have this MLP, this multi-layer perceptron, that has encoded the whole 3D scene, so every single information about that scene inside of the weights of that MLP. So that's kind of crazy and an interesting paradigm if you've never seen NeRF before. So, but in a nutshell, that's it. You have an MLP, you take a bunch of rays, you query the MLP alongside certain points, you do the MSE loss, and that's how you train the NeRF. And it took, I think, in the original paper, somewhere around like 7-8 hours wall clock time to train this thing to kind of memorize a single scene. That's cool. Here you can see the thing I was mentioning about how we actually accumulate the colors along this particular ray, and the whole trick is to form these coefficients TIs. Let me change the color here. So TIs are just this sum, and we have the minus here and the exponent. So it's exponential function. And so what you can think of this the following way. So as I said, once you get inside of the bulldozer, the thing is, this TI is gonna be very, very small, and that means that the color inside of the bulldozer is gonna be weighted with a very small number here. So that's gonna be approaching 0, which means that the final color, this C hat, is gonna be heavily influenced by the first points that are close to the surface of the bulldozer, whereas the other points are going to have less influence, which makes a lot of sense. So again, these deltas are just these distances. Let me kind of zoom in here. So delta J's are just the distance between these successive points here that we are sampling, and the sampling here seems like to be uniform, but in reality they're using stochastic sampling so that we can query the NeRF, the MLP later on continuously across this whole space. And you can see basically that as sigma goes up, that means we're entering bulldozer, this thing is going to be bigger and bigger, and because we have a minus sign, we just have an exponential. When you have the minus, that basically means this thing is gonna converge to 0, and that's what I just explained. So hopefully that makes a bit more sense how NeRF works. So that's one approach, and that's called implicit scene representation, and it's implicit because the whole knowledge of the 3D scene is encoded inside of the weights of this multi-layer perceptron network, and that's very cool. A bad thing about this approach is that even though the whole scene is encoded in a relatively small number of weights, if you want to render a single pixel, so imagine we are now here and we don't have the actual pixel value, we'd have to query the MLP across all of these points, so that's a single forward pass times n, because we have m points sampled along the array, in order to get a single pixel in the image space. And we have to repeat that for every single pixel in the image space. So you can imagine that's kind of time intensive, okay? So that's where these second family of approaches come into play. What they do instead is they explicitly keep the information about the 3D space, as you can see here, visualized in form of this cube. And that means this approach is expensive memory-wise, but it's much cheaper to do an inference here in this model, because you don't have to do a forward pass, you already have it explicitly stored, you can just kind of average it out and get the color of the pixel. So that's everything I want you to take out from this image and explanation. By the way, I've put here inference prediction because there is a lot of, just to point out that people are very sloppy with terminology in general, so we should be using probably prediction would be the correct terminology here, not inference. Inference is more came from the context of probabilistic models, and yeah, but people use these two interchangeably, even though in reality we should be using the word prediction instead of inference. But yeah, super small digression there. Okay, so now that we know the trade-offs, let's see what the actual paper brought to the table. So we can see here what they did. Instead of storing every single like RGB and the volume density in the scene, they just have these 3 planes. And even though these look like slices of paper, they actually have the depth dimension, because they'll have features here, like maybe 32 features alongside this dimension, and every plane obviously will have like the depth. So this one we'll have here, and we'll have here, like maybe 32 features, but that's still way less compared to this model here that has this. So it's, I think they call it, yeah, explicit voxel grid approach. And again, so it's memory. It's more efficient memory-wise, and it's also more efficient time-wise, because as you can see here, to find the RGB, so to get the RGB value, the color, and the volume density, we just have to pass it through this very shallow MLP and compare that to NeRF, where you have this huge like MLP. I mean relatively big compared to this approach here. So now the question remains, so that's all nice and sweet, but the question is this as expressive as these models here? And the answer will turn out to be yes. But before that, I forgot to mention how this is constructed. So if you want to query the scene and get the color at a specific point in the scene, what do? You have this point, you basically project it onto these planes. That means you'll have in our case, we'll have a 32-dimensional vector here. So that's going to be 32-dimensional vector, and then you extract the vector from here and from this projection. So this is maybe XY plane, and you just basically add them up, and then you pass them through a couple of fully connected layers, basically a multi-layer perceptron here. So that's how the thing works. Now, we need to make sure that this is as expressive as the two other approaches, and that by creating this more efficient model, we haven't sacrificed the quality. And it turns out that we have not. As you can see here, the 3-plane approach, so that's the one here, has a higher quality. The letters are much more readable compared to the 2 other approaches, which is very, very cool. That means we've kept the expressive power of the 2 approaches, and we made the model more efficient. So what has happened here is that they are basically, in this particular example, the trainable weights of this model are these weights contained in the planes, as well as the weights of this fully connected of this FC layers. And the way they kind of trained the 3-plane model is the same way I just explained for NeRF. So they use the same approach to train an overfit on a particular scene. In this case, they have this scene called family scene. So they train this component here the same way as you train NeRF, and they have to tweak these weights in in these 3 planes. And it's going to change in the actual final model that I'm going to explain right now. By the way, short digression, as I said, these 2 papers would be useful to have some prior knowledge on, and hopefully I gave you enough context for you to understand the rest of this paper. But the 3rd paper we're going to find very useful is style GAN. So I guess the version 1 and 2 will suffice. These kind of had incremental improvements upon the first version of style GAN, which had amazing results. So let's get to the actual final pipeline. I've explained, we now understand this part here. We understand this whole part of the pipeline. So let me kind of encircle it, square it here, whatever the name is. So you can see we have these 3 planes. We get the color and the density, and because we have the camera parameters, 25 scalars, we basically can render the image from whatever pose in the scene. So that part we understand. And by the way, it's 25 because it's 16 for the extrinsics matrix, plus 9 for the intrinsics matrix. Extrinsics means that it basically just maps from the global, from the world coordinate system into the camera coordinate system, and the intrinsics are there to map from the camera coordinate system into the image space. So that's some basic computer vision theory for you. You don't have to worry too much about it. But basically, these 25 numbers tell you how the camera is placed and tell you certain properties about the camera. So how it's placed in the scene and certain properties. So the approach will basically be to, you're in the scene, you're basically in a 3D scene, you place a camera somewhere, and what you do is you emit a bunch of rays and you sample a bunch of points alongside those rays. So let me just kind of change the color. So you'll sample a bunch of points, and all of those points, so when you query those, you'll get as the output, you'll get the color and the density, the volume density, and then you combine them in the smart way I just showed you to get this final image here, which is 128 times 128 times 32, which is different. So it's not an RGB image, and the reason they've done it like this is because it's more expressive, and we'll see the details a bit later. But that's this component of the system. Now let's switch our attention to the first part here. What happens is they basically reuse the generator from the style GAN paper I mentioned. So it's your classical GAN architecture, albeit very, very smart one, where, as you can see here, we have a latent of 512 scalars. So you have certain vector, like some noise vector, or I think it's actually trained in the case of style GAN. You input that into the mapping vector. The mapping vector creates these intermediate representations, which we can then use to condition the generator here, which, as you can see, is upsampling in every single layer. We're doing some we have some deconvolution, so-called deconvolution layers, and we end up with this image 256 by 256. That's a spatial resolution, and then we have 96 features. And what we do is we just take the 96 features and we split it into 3 planes that each have 32 features per plane, and we kind of just visually represent those here, and then we know this part here now. Now, the interesting part I want you to see here is that camera params are used to condition the mapping network, because that helps the generator decouple certain post-correlated features and, in general, increase the expressivity of the generator. I'm gonna probably show you a bit later what I mean by the correlation between pose and features, but basically what it means. Let me see whether I can find the maybe somewhere in the appendix. Basically, people tend to smile when they're facing the camera up front, and they tend not to smile when they're not facing the camera. Let me see whether I can find that curve. Oh yeah, okay, I found it here. So basically, you can see here the plot that tells you. So yaw is just basically tells you how rotated the head is alongside this let's call it XY plane, and you can see that when you're facing the camera like up front, the percentage of smiles is way higher when compared to when the head is turned away from the camera. And the reason is fairly simple. When people know that they are being photographed, they smile, and when they're unaware, they're just being themselves and they're not smiling, because let's face it, this world is not that happy, right? It's a very sad world. Anyways, enough with very, very bad jokes. Let me go back to where I stopped. So we are here trying to understand this whole pipeline. Hopefully now I managed to kind of break down this first component of the pipeline, which is based off of style GAN. The second part is based off of, as I said, some combination of NeRF and those explicit grid methods. And finally, we have the third component here, and let me now try and address this part, and then you'll understand the complete method. So what I've done here is once they do the neural rendering and they have this 128, 128, 32 volume, if they extract the first 3 channels, those will actually be representing the actual image. So those will contain, by the way of training, those will contain the downsampled version of the final output image. And so what they do now is they upsample the image. So they'll upsample the first 3 channels using basically bilinear. So bilinear, let me try and write it down, bilinear transformation, which is not a learnable transformation. That's just your classical digital image processing upsampling method, nothing fancy there. Secondly, they'll take this whole volume, all of the 32 channels, and they're going to pass it into this super resolution module, which is going to upsample the image, and out comes the 512 by 512 RGB image, so 3 channels. And again, we have some conditioning here. They're using these intermediate latents to condition the super resolution module. Not completely sure whether whether they did some ablations, but like it makes sense that the information used to generate the original image, I mean, it's not the original image, it's just these features that are then neural rendered. So yeah, I'm not sure whether this was ablated, but like whether it will work as good without this part, but yeah, it works like this. And what happens now is they just take and concatenate the upsampled image and this this image that was passed through the super resolution module, and then they pass it into this style GAN 2 version of discriminator, which is your classical GAN loss. You're trying to figure out whether the image is real or not real, because you have some data set. You basically have some data set of real images that's going to help you figure out this fact, whether it's real or not. Additionally, we are again conditioning the discriminator using the camera parameters, so the extrinsics and the intrinsics. Now this is called, what they call this is the double discriminator or something like that. We're going to see the terminology a bit later. But the point is, they're going to, by concatenating and having 6 channels here, what they'll have to do is the following. So they'll take some real image. So this is a real image. And then they're going to downsample that image like this. And now they're going to use, and that basically means that this discriminator is going to force this neural rendered image to be the same, to be realistic as these downsampled real images, and it's going to force like the big image to be realistic as the big images here. And all of these constraints help the model learn how to be consistent in various poses. And one of the crucial parts is actually conditioning on these camera parameters. I forgot to mention how they actually have, so some data sets do have this data, so the extrinsics and intrinsics. In other data sets, basically they made an assumption of how intrinsics are what intrinsics make sense. We're going to see that in the appendix a bit later. And they use some off-the-shelf detectors to figure out the pose, so that means to figure out the extrinsic component. And that's how basically they train this whole thing. So yeah, they don't have the 3D scans, but they do have the camera parameters. Keep that in mind. Okay. Okay, now that should be pretty much it. You now should understand how the whole pipeline works, but let me go through some additional details. So here, this table, they just show the thing I mentioned about the trade-off between speed and memory. This novel approach is both faster and more memory efficient. One thing worth mentioning is that the 3-plane representation is capable of representing this complex scene, albeit without view-dependent effects. That's what I mean by that is that in NeRF, you can change those theta and phi angles and get different color depending on how you're viewing the scene, and that kind of helps you model the glossy effects, the non-labertion. I think that's the fancy way from the computer graphics world. So basically, let me see whether, yeah, there is a visualization of NeRF somewhere here. So here it is. You can see that the color here depends on the position and on the direction as well. So the direction meaning the theta and phi angles. So even if you're even if you're in the scene in a certain position, like here, depending on how you kind of direct the ray from that point, you're going to have different colors. Because of the way that NeRF is set up here. Whereas, as you can see here, the density, the volume density is not a function of the direction, which makes sense because density just tells you whether the ray will stop at that particular point in the scene, and that should not depend on the direction. So if you're inside of Bulldozer, you're inside, and it doesn't matter the direction. This density should be high because you're inside of an object that's not, unless it's transparent. Okay, but yeah, modeling transparent objects, that's I guess a separate league. Let's continue. So I explained that part. Now I mentioned the consistency that the double discriminator brings to the table. Now let's see what they said here. First thing they say here is that the real images are fed into the discriminator are also processed by concatenating each of them with an appropriately blurred copy of itself. So what I mean by that is that once you have this small image, once you downsample it, you'll have to upsample it again, and by doing that you're gonna lose some details and the output image is gonna be somewhat blurred in order to be able to concatenate it and create this 6-channeled like input volume. So this is the real image. It has 3 channels and have certain spatial dimension, and this is the upsampled. So we first downsample and then upsample the image in order to mimic the process here. Okay. So what they say here is that they are just kind of blurring, and basically it should not be. So the way they're probably approaching this is if you do like take an image of the full size and then you downsample it and then you upsample it again, I'm fairly sure that if you go into the spectral domain, you can just devise a kernel, a certain kernel, like a kernel like in the sense in convolutional neural networks, you can devise a kernel that's gonna modify the spectrum of this image in such a way that we get the same effect as if we were to downsample explicitly and upsample again. But that's just a implementation detail that would probably make this process a bit more efficient and optimized. Okay, so the terminology I was trying to get at was the dual discrimination. That's how they call it, and it not only encourages the final output to match the distribution of real images, but also offers additional effects. So it encourages the neural rendering to match the distribution of downsampled real images. So that's, remember why. So neural rendering to match the distribution of downsampled real images. So that's because, as you can see here, so this is the neural rendered image. So this thing here, so as you recall, we basically took the first 3 channels and we get this. And now once we upsample this, we are basically making sure that this thing looks as close as this real image that was downsampled and upsampled. Okay, so that's why we have this consistency constraint. And it encourages the super resolved images to be consistent with the neural rendering. And what they mean by that is that basically this image here is going to be encouraged to look the same as this image here, which means that the super resolution is going to do its job. Basically, it's going to just upsample the image without modifying the pose or the appearance or whatnot of this output image. Okay, so that's it. Let's now continue and let's see some results. Results are fairly stunning. You can see the identity of this man looking frontally, and then when we change the pose, you can still tell that this is the same person. And similarly here. So this thing with the eyes is a bit creepy. It doesn't look like this person should be watching at the camera. Looking at the camera, it looks like the eyes should be going there or something like that. But yeah, looks kind of weird. We're gonna see why that is a bit later. Basically, there are some problems where the underlying geometry of the eye socket is concave instead of convex, which is creepy. They compare with the baseline models, and as you can see, every one of these has some problems. Either the geometry is super bad or it's super like very like smooth. And here it's also, you can see it's the image does not look realistic. The teeth here are smoothened out, and the geometry as well. And here is this method, the proposed method, looks way better compared to the baselines, just qualitatively analyzing these images. Quantitative analysis showed the same thing, comparing with these baselines, looking at a bunch of different metrics. I'm not gonna get into what these metrics are. FIT, basically Fréchet's inception score, like depth, and they're just comparing geometry and the quality of the generated images. And you can see that this approach is way better compared to the baselines. They also compare the speed, the number of frames per second, and you can see that it's lagging a little bit behind GiraFfe and some of those methods, but as you saw, the quality is way better, so that's kind of decent trade-off. Finally, they use this FAC-SMILE, like STD, I guess it's a standard deviation. I think this just kind of shows that the multi-view consistency is better when you use the dual discrimination and the adding the generator pose conditioning, the GPC, to the model. So that's the basically the camera parameters that we were feeding into generator to condition it. So that was this part here. So using this conditioning on the parameters, the generator, the mapping network part of the generator, that helps a lot incur this consistency. Okay, let's continue and see some results. So this is, I'm gonna skip this. This is from the style GAN. This is already very clear from the style GAN papers. You can mix up the style from the row. So this person here dictates the style, and these persons in the column dictate the general geometry and appearance. You can see they're kind of mixing up this kid here. You can see how the style of the kid is changing depending on the leftmost column. Okay. I thought explaining how this PTI works in more details, but it's gonna make this video too long, so I can maybe cover this separately in one of the next videos. But basically, what I managed to do is, given the image, the desired target image, they managed to find the latent that generates that image, and then they can basically modify and edit the image semantically inside of that latent space. So that's very cool. So what you can notice here, I mentioned the concaveness of the eyes, and that's the reason why it always looks like the eyes are looking directly into us, directly into our eyes, whatever, is because you can see that the eye sockets are kind of concave here. I think they mentioned that somewhere down here. Let me find it. So furthermore, ambiguities that can be explained by geometry remain unresolved. For example, by creating concave eye sockets, the generator creates the illusion of eyes that follow the camera, an incorrect interpretation, though the renderings are view consistent and reflect the underlying geometry. Okay. Not gonna dig deeper into that, but I'm just gonna first address this paragraph here because I think it's also important, not that like related to this concrete paper, but I think it's in general, I have this, are these paragraphs useful, asking myself whether this is useful. I'm gonna read it out loud so you can judge yourself. So the single view 3D reconstruction or style mixing applications could be misused. So it could be misused for generating edited imagery of real people. Okay, we are all familiar with deepfakes, with that GANs are in general kind of problematic in that sense. Such misuse of image synthesis techniques poses a societal threat, and we do not condone using our work with the intent of spreading misinformation or tarnishing reputation. I mean, that's also kind of should be obvious. Authors do not want their paper, their work to be used maliciously. I don't see any added information in these sentences. And finally, we also recognize a potential lack of diversity in our faces results stemming from implicit biases of the data sets we process. And this same sentence could be copy pasted into so many different papers. Like, let's replace this 3D GAN paper, let's replace it with like a GPT-3 or whatever your favorite language model is now in 2021, maybe Voodoo 2.0 or something, I don't know. And basically, so it also can be misused, and secondly, the authors condone using their work maliciously, so that's also true. And it also is true that depending on the biases in they basically use the text dataset that was collected from the internet and Reddit, which has a lot of biases for like various things, like for example, Muslims being associated with with terrorism, stuff like that. So some bad societal biases. So the point is whether we should just be copy pasting this everywhere, because this can be applied for every single paper. Yeah, I don't mean anything bad by saying all of this. I just want to kind of raise the concern of whether this is going to be of any practical use, paragraphs such as this one. I'm not sure. I'm not smart here. I'm just speaking out loud here. Finally, let me just find one additional thing here in the appendix. It has to do with the intrinsics. Okay, here it is. They say that we assume for the FFHQ dataset, which is the dataset of those high-resolution human faces, not the cats. The cats are this is the cats dataset. So they say we assume fixed camera intrinsics across the entire dataset with a focal length of 4.26 times the image width, equivalent to standard portrait lens. So that means that's kind of assumed. So that means it might not be correct. I'm not sure how the dataset was collected. So it may happen that different images were collected with different cameras, which means this would not hold as a hypothesis. And they are using certain off-the-shelf detectors to figure out the extrinsics. So I haven't seen, not sure, I may be making a mistake here, but I haven't seen any ablation on how robust the pipeline is to the errors in this if this turns out not to be the case, that this is a correct intrinsics for this data set. Yeah, I just thought kind of mentioning that. Also, one thing I'm not completely sure is how they're generating these geometry visualizations. I can assume that, let me just go back to the pipeline here. It's going to be easier to explain what I mean. Okay, it's a long paper. Okay, what is probably happening is that they are using the density information. So they pass a ray through the scene, they have the density information, and they can kind of do a threshold and aggregate that density information. So maybe these charts will be even better. So they have something like this, and then they can just kind of threshold the density, and then use that to generate the geometry. But I'm not sure whether, I'm fairly sure that will have a lot of noise and glitching. So it'd be nice to kind of, for people who do not do this every day, including me, it'd be nice to have some hint of how stuff is done, because understanding how geometry is actually visualized seems to be fairly important. Anyways, if somebody knows exactly how this is done, feel free to comment down below, and hopefully you like this video. Let me know whether the lack of camera is ruining the experience for you guys. So I'll make sure to, in any case, bring it back very soon and create my YouTube studio here in London, hopefully in like a couple of weeks. In any case, subscribe if you like this video, share out the video with friends, and join the Discord community, because there is a lot of awesome, cool people there which are willing to help each other out. So consider joining the community there. And until next time, bye bye.